welcome back. So we continue Francesca's lecture.
We continue and we finish Francesca's lectures. So we arrived to the end of this. Yeah, and I kept my favorite thing for the end. So the application of all the things that we have discussed in the past 4 hours to cosmology. And then, of course, for a continuation of this conversation, I look forward also for the lectures by Hong Guang on numerics and the lectures by Carlo on black holes. But let's talk about cosmology, maybe. Okay, and in order to talk about cosmology, again, this is an unfortunate setting of the lectures, because you will have a full course on loop quantum cosmology in the next days with Param Singh, in which you will learn the way in which quantum cosmology is usually established. So the development of quantum cosmology in general came as a way to make sense of that famous path integral, the sum over the integral over histories that we saw before, when people still didn't know how to solve the full theory. So then going to a symmetry-reduced sector of GR was a way to simplify the calculations. So instead of taking the full metric, you reduce your metric to the cosmology one, in which basically you reduce the full degrees of freedoms of general relativity to just 1 degree of freedom, because you describe everything in terms of just the scale factor, namely the volume, how things scales in your system. So then the idea was that these degrees of freedom, just single one, is easier to quantize, and then maybe you can quantize also some more degrees of freedom, some inhomogeneities, some anisotropies, and you get to quantum cosmology in this way. And of course, back then, the idea was in quantum gravity, in loop quantum gravity, was to try to get as close as possible to this procedure, just mimic the same thing. So go to the symmetry-reduced sector and quantize a la loop my scale factor. So this is what has been done in loop quantum cosmology. The first paper appeared, Param will tell you about this. The first paper appeared in 1999, appeared on the archive, and was published in 2000, so it's easy to remember. The new millennia opened with the loop quantum cosmology, and then it took a few years really to figure out some details. So what Param will present you in the next lectures will be the version that was developed by himself with by Ashtekar and Thomas Pawlowski, in which they were able also to do numerics, by the way. And this was also one great achievement in the theory introducing numerics in loop quantum cosmology. And people were able to see that if you were propagating a coherent states, that in the case of cosmology is just a simple Gaussian. So you propagate these states, and you see that it's peaked on classical solutions for a large universe. But then if you go back in time when the universe was small and dense, there is a deviation with respect to the classical dynamics. So instead of having a Big Bang, you have a bounce. So your equations jump into from one solution, from a contracting solution into an expanding solution. So you can think about this as a tunneling. And so you can continue the evolution of your universe, or vice versa, if you look back in time, you can think that our universe is in fact emerging from a previous phase in which the universe contracted, and now we are seeing the bouncing phase, the out of bounds phase in which the universe is expanding again. And the equations are beautifully the corrections at the effective level is so simple. Is this correction that you see here, in which you have a correction here. So it's just it's a correction that kick in when your energy density rho is close to a critical energy density that is taken to be at the Planckian energy density. So this is the standard Friedman equation that you should, this part is the standard Friedman equation that you should know from your basic courses in relativity, in cosmology. And here you have, at the end of the day, simple corrections. And it's a simple corrections that appears also when you look at the perturbations. So perturbations are one of the most important, is basically the most important observable that we have in cosmology. And we wanted to study how perturbations evolve in time. And we wanted to match whatever predictions our quantum gravity theory in the deep quantum regime says with the observations that we have for perturbations at later time out of the quantum regime, namely what we see in the CMB, for instance. So you can write down evolution equations for these perturbations, and that are the Mukhanov-Sasaki equations. And here as well, you have the appearance of these simple corrections. So this is all beautiful. This is all achieved using, of course, states that are not exactly the spin network states, but they are still valued in SU2, in the group. You use the information from the observable of loop quantum gravity, namely the presence of this minimal area. You use the Hamiltonian constraint quantized that Christina has introduced, in which you can have corrections from the holonomies, the quantization of the holonomies, and you can also have some corrections from the volume operator that appears in the denominators of the equations. And the magic is that you can have a lot of results there. You have singularity resolutions. As I said, you have a big bounce instead of big bang. You have the modified Friedman equation. You have the modified Mukhanov-Sasaki equation. So I'm not going to summarize here 25 years of research. Param is going to do that. What I wanted to do instead okay. Let me just skip this that I have already said. Well, as I say, more results that appears in these slides, including the fact that in most of the calculations, what you see is just trying to get as close as possible to what is done in standard cosmology. So, for instance, using an inflaton as a matter content for your cosmological models. This may not be necessary, and I just highlight this because you may want to see some of the talks, including the talks by my collaborators and students and postdocs during, like Emmanuel Frion and Matteo Pasquale during the conference later about this. But, so, let's go back to our business. So, this is just to frame the situation, and of course, my motivation at the beginning was saying for this picture that I gave you was people didn't know how to quantize gravity, so they were doing this as a model, a simple model of quantization. But I just told you that we have a theory of quantum gravity. It's a tentative theory, but it's still a well-defined theory with which we can do calculations, and that's exactly what we want to do in cosmology. So instead of going through the symmetry reduction, what we can do is first to go into the full quantum theory, and then see how we can we can find a sense in which we can recover a cosmological sector within the theory, okay? By the way, at the canonical level, a lot of work in this respect has been done by Jonathan Engel, so you can ask him about that. What I will focus here is something a bit more mild than what Jonathan did. So let me tell you. So instead of using the canonical dynamics, we want to use the covariant dynamics. And of course, this poses a problem because while before I told you that in loop quantum cosmology, what you can do is to evolve some wave packets, and you can see how the wave packets evolve through the bounds. Here, I don't have trajectories, so we are in a full quantum theory in which we compute transition amplitudes. So we have an initial states and a final states. I can give you probabilities from going from one to the other. So connecting with what we know from standard cosmology requires a bit more thinking, let's say. But I will show you that this is possible. So we can use the full techniques, the full results that we got from covariant loop quantum gravity in order to study cosmology. This morning I told you about the possibility to discuss a singularity resolution in this context. But in general, the advantage of going through this procedure is the fact that since we are in a full theory, we are not taking any approximation. So if we are able to describe a state of the quantum geometry that corresponds to a cosmological sector, this is something that is valid in whatever is my bound state or Big Bang state or whatever. So we are beyond the regime in which you are taking approximations, you are forgetting pieces, you may disregard some aspects of the quantization, and instead you have something that is fully valid in the deep quantum regime. So we can try to study fluctuations, we can study quantum correction to the classical dynamics in this context. Now, in this lecture, I wanted to talk about this, give you a bit of history of the different results, and I want also to talk about results that are pretty recent, like from a few months ago, and tell you a bit where I see that we can evolve further this program. First of all, we wanted to exploit everything that we have been using in the theory, in this covariant theory. And so let me start from the kinematic of the theory, namely my graph states. The graph states at the kinematical level. So something I tried to stress in the lectures was that, so the graph is a truncation. And a truncation, it's something you introduce by hand, and you choose a good truncation depending on the kind of physics you want to describe. Oh, now, think for a second what you do when you do cosmology. So doing cosmology is about describing the universe with just 1 degree of freedom, with just the scale factor. This is basically what the great illumination, how to say, the great enlightenment from Einstein. You have the cosmological principle. So it makes sense to describe the universe as a whole with just the scale factor. That means, okay, maybe you need just a single node to describe the whole universe. You have to describe the evolution of just a single node. So, but this is a bit too trivial, okay? So we can do better. Like we can use 2 nodes. And then you can try to understand how many degrees of freedom do I have if I have 2 nodes? Well, you start to have 6. So that is already much more than what you have when you do, for instance, Bianchi models in which you have 3 independent spatial directions. So you have, so even if you take just a triangulation of your space with 2 nodes, you are already in a situation in which you have a model that is more rich than what is usually done in cosmology. A good choice could be, for instance, to take a nice regular triangulation of a 3-sphere. So, okay, most of the time we think of the universe as being flat just because it's easier, but I said this morning we like finiteness, so maybe the universe, as Einstein liked too, is a 3-sphere, okay? So if it is a 3-sphere, assume it's a 3-sphere. We can triangulate a 3-sphere, so we can chop the 3 spheres in the most regular way, and this corresponds to take 5 tetrahedra glued together. That means that you have a graph like this one. So for each node I have a tetrahedra. Tetrahedra has 4 faces, so you see here I have each face that is glued to another one of the other tetrahedra. So, for instance, a simple graph like this could already be a very nice truncation of my theory if I wanted to do cosmology. It also has the nice property that if you put yourself in one of the nodes, so each node here has the same degree. That means that it doesn't matter where you are, you see the rest of space-time as being the same. So this is exactly the definition of isotropy. Another thing you can do is take all the spins being the same when you define the quantum states of this graph. And in this case, this is something that basically may be a proxy of what you mean by homogeneity. And keep in mind that when we take these choices, we are approximating a geometry that is homogeneous and isotropic, or more precisely, what I can do is, instead of writing a spin network states here, I can write a coherent states. So a coherent states can be picked on a homogeneous and isotropic geometry, but when you do so, you still have all the fluctuations of the quantum states. So it's not a rigid way in which you impose homogeneity and isotropy. You just take homogeneity and isotropy as an approximation of what happens in the universe, and you let some quantum freedom to be there. So depending on what you want to describe, you can choose different graphs, and we have said that the full theory is recovered when you have a graph that is infinitely complicated. But this is not what we do here. Oh, by the way, a nice description of this is in this paper, or even better, there is a paper of mine that is called Relational Quantum Cosmology that I recommend if you wanted to think more about this. So the fact that we can use a very simple graph, or if you think what is dual to a graph, we can use a very simple triangulation to describe cosmology. Well, it's not something new, it's not something that we have invented. In fact, this was done a long time ago in Reg calculus. So here, for instance, you see you have a single tetrahedra that evolve, or in this case, again, Ruth Williams with a student was considering, again, this is a numerical work, again, one of the infancy of numerics in quantum gravity. So in this work, they were doing exactly the same that I was telling you about. So taking different regular triangulation of the three spheres, and unfortunately, so if you wanted to stay with a regular triangulation, one in which all the tetraedra are the same, all the angles, all the area are the same. Well, you can do this with 5 tetraedra, and then the next regular one is with 16 tetraedra, and the next regular one is with 600 tetraedra. So the scaling here gets a bit wild. So what I will do, and what we have done also with spinform models, was to focus on 5 and 16. You will see this later. Anyway, in Regge calculus, you can achieve this. You can arrive to the 600 tetraedra, and so you say that qualitatively, the evolution of your universe is not changing. Okay, so these slides is not meant to be discussed. The only thing that I wanted to say here is the fact that you can approximate a homogeneous and isotropic geometry with coherent states, and in particular, you may want to use extrinsic coherent states. So you know, I have already told you that you have intrinsic and extrinsic coherent states. The extrinsic ones are a bit more complicated than the ones that I presented to you, but they have the advantage that they are equally spread in position in the three geometry, but also in the four-dimensional geometry. So this is just to tell you that when I will talk about coherent states later in my discussion, and also I believe when Hong Wang will discuss things later, we'll use coherent states of this kind. Yes, there is a question there. I don't want to stay.
Yeah, I had a question about this picture there. Why is it changing signs? Basically, why is it going down again?
Oh, well, because in this case, so in this picture, what is happening is a collapse indeed, but I don't have the details of the dynamics of the choices that they made there. So the only, I apologize because, yeah, this is actually a old work, but the point is that, so what I wanted to show with this picture, the only thing that I want you to remember from this is the fact that when you change the triangulation, you have the same kind of behavior. I don't remember why they are collapsing here. Okay, good. And so the first thing that we did back then when we tried to apply the spinform dynamics to cosmology was to use one of those coherent states, use the brand new back then APRL vertex, and cosmology provided us a framework in which we could check the classical limit of the theory. So this is my highest, so I will present more work that is numerical. This is my brightest contribution to numerics, in which I proved that that the spinform dynamics computed with the coherent states picked on homogeneous and isotropic geometry and with a cosmological constant was picked on classical solutions of the Einstein equation, namely where A dot is proportional to A. So you see this. So back then, adding a cosmological constant was the best we could do to add, instead of just adding a scalar field. But now we have better technologies. So this is a very recent result. In fact, is mostly the work by Dongxue Ku. who figured out how to describe a bouncing universe. So in this case, we are not taking a tree-sphere, we are taking the geometry of a torus that we are triangulating as an hypercube. And in fact, each of these have 16 nodes. And beautiful results there is that you can take one hypercube that has a certain intrinsic curvature that corresponds to a contraction, and then you can take another hypercube that corresponds to in which the intrinsic curvature corresponds to an expansion. You can use the spin-foam dynamics to compute the probability for going to one to the other, and you discover that the probability is not zero. That means that there is a bounce. So careful here, because the two solutions are disconnected in the classical theory. So in the classical theory, it's forbidden to go from one solution of the Einstein equation, that is the contraction, to the solution of the Einstein equation that corresponds to an expansion. The only way in which you can connect the two solutions is when you have a tunneling. And notice that a tunneling is a prototypical quantum phenomena. It's something that you cannot capture with perturbative physics, okay? So you need the full quantum theory to do this. And this is exactly what the spin-foam dynamics does for you. The amplitude is suppressed, as I said, because in the spin-foam dynamics, the amplitudes that are not suppressed are the one that corresponds to classical solution. But then you have a non-zero probability to have one of these phenomena, tunneling phenomena, that is characteristically a quantum one, so that there is a non-zero probability for the bounce to happen. And of course, the idea is that when you go into the deep quantum regime, where classical solutions are not accessible, then the probability of having an evolution that is the quantum one, the tunneling one, is the one that dominates. So this computation, was there, yeah, questions. So just let me say that this computation is done using semi-classical techniques, and the beautiful thing is that in this context we were able to find corrections to the Friedman dynamics, and what comes next will be to import these corrections in a standard cosmological model and see what they give. Yeah.
Thank you. Yeah. In the effort of the universe, and for an early universe, it should be the Asian domain. But here you see that they only consider the contribution of the matter field. So how about the contribution of the radiation?
So if I understand your question, the problem is that I'm talking about something that happens in the early universe, right? So, but the states that I am considering are semi-classical states, right? Mm-hmm. So the question is the interplay between these two things. How do they stay together?
But I mean, for an early universe, it should be the radiation domain.
Sorry, it should be?
The radiation domain.
Radiation dominated.
Oh!
Yeah. Yeah.
Yes. So what?
But yeah, you only consider the contribution of the matter.
No, careful about something, because even if, okay, when you do cosmology, first of all, the bounce is not necessarily radiation dominated. It's in standard cosmology, but it is not a necessity. The other, it could also be, by the way, dominated by a cosmological constant or by exotic matter. Anyway, this is independent from the kind of calculations for the gravitational field that I am doing right now.
Okay.
There is another, let me try to see if the other questions maybe are also helping to answer to this question.
Thank you.
Yeah, sorry, but we can get back to this later, okay?
Okay, thank you.
Yeah.
Thank you. So you mentioned that the probability of this tunneling happening is the dominating situation.
No, I'm saying something else.
Okay.
I'm saying that the amplitudes in spin form are maximal when are always peaked on classical solutions. So when you have a process that involve going, so imagine you have something you know, like, I don't know, the universe that has a certain size, and then the universe that has another size at a later time. So this is perfectly described by a classical evolution. So I perform my computation in spin form, and I see that in that case, the amplitude is very high probability, almost one probability, something like this. But then what we are interested in is where, so one thing is to probe the classical limit of the theory. So we wanted to check that everything goes well, that amplitudes is peaked on classical solution, very nice. Okay, and then, but then this is just the classical dynamics. What we are interested in is when my states are outside of the classical dynamics. So I wanted to check for instance, all the parts in which the amplitude is suppressed, so the probability is very low, but it's not zero. So this is exactly where you have a tunneling, like it happens all the time in quantum mechanics. Does it make sense?
Yeah, so let me
And
see.
maybe Carlo will talk more about this also later.
Okay, so let me see if I understand. So the bounce is the tunneling situation, right?
Yes.
There are other solutions which don't have tunneling. So my question is, in this case, what is exactly happening? Like we don't have a resolution of the singularity for those solutions?
So, no, okay, so first of all, you have another information from the theory that says that you cannot have an infinite curvature. So it's like at a certain point, the evolution, the classical evolution is stopped somehow. And it's like this is a kind of evolution that is not accessible to you. So like you are exhausting, the more you go into the quantum regime, it's like the more you are exhausting all the possibility to evolve into something classical. And at a certain point, you reach a point in which no classical step forward is available, and then you look for what else is possible. Oh, yeah, there is this little probability here that now is the only one available to go into that other thing, and so you tunnel.
I see.
I don't know, that's the best story, the best narrative I can make. This is the way in which I picture this in my mind. I don't know if, Carlo, yeah, you wanted to say something. Maybe with the microphone so everybody can hear.
I think it is. Think of an electron, which a wave function, which is a spherical shell, which is following on the nucleus of a hydrogen atom. We know the classical solution. It just falls inside and then dies. Okay? And quantum mechanically, initially it's exactly the same, but then there is a probability of something else to happen, which is the bounce, exactly the same bounce, right? There is no infinite fall toward the center of the atom if you can dissipate the energy, you stop on a minimum energy state of the hydrogen atom. If you have energy, it bounces, okay, whatever. But even if you have zero angular momentum, so it's not rotating, the only thing you can do is bounce. So the way I think about it, it's a good question, I've been thinking over and over, is that imagine splitting the time interval in an infinite number of shorter and shorter intervals. And at each one, you have a probability of going to the next or quantum jumping to another solution, and the only other solution which has, by conservation of everything, is its bounce. So the more you go up, the more the probability of jumps go higher, 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 higher. So this is what Francesca was saying. When you integrate it, you have a probability 1 of going back. So what you're actually computing is the probability of jumping earlier or later.
Good.
Thank you.
And again, you will see another computations in which you have this with the black holes tunneling into a white hole. So there will be opportunity to reflect more on this. The next thing I wanted to tell you here is this. So I told you that we have spin form a vertex expansion. So you have 0 vertices, one vertex, then 2 vertices, 3 vertices, and so on. So 0 vertices is just the identity, nothing happens. We focus on the one vertex case. And the one vertex case shares a similarity to the first order approximation when we consider semi-classical dynamics. So when you consider just the standard action for the cosmological case, with the cosmological constant here, you see that the action, in fact, the Hamilton function factorize in, sorry, it doesn't factorize. So it is given simply by this difference between the initial and the final volume. And this is reflected in a factorization in the transition amplitudes that you can compute with this object. So the amplitude factorized in the probability of the universe to have a given scale factor and the probability of the universe to have another scale factor. So this factorization is just an effect of the approximations that you are doing. But I am stressing this because this is exactly what happens also with the spin form amplitudes. So, as I say, you can have a 0 order, you can have then a first order. And so, in the first order, what you wanted to compute, when you compute the transition amplitudes between an initial state of your quantum geometry that represent a homogeneous and isotropic universe. So remember, I told you that this 5-valent graph can represent a 3-sphere, a regular discretization of the 3-sphere. So suppose I want to go from one 3-sphere to another 3-sphere. In the first order, I have just one vertex, and the amplitude factorize into the probability to go from one geometry into nothing, and from nothing into a given geometry. So then, this is exactly the definition of a Hartog-Looking state. So the Hartog-Looking state is defined as a no-boundary picture in which you just take a 3-dimensional geometry and you sum over all possible 4-dimensional geometries that are compatible with that particular boundary. The nice thing that is happening here is that now I can use this object as a state, because this is a three-dimensional geometries in which I don't have just a spin network. I have a superposition of spin network. But somehow, this particular state is the one that is chosen by the dynamics. Remember, my amplitude is basically projecting on the physical states of the theory. So I can use this object as a state, and I can study the property of this state. And in particular, what you may want to study to do cosmology is to study correlations. What does it mean to study correlations? So in the universe, you have fluctuations of your geometry. For instance, if you have a matter field, you can have the matter field that has a certain value here and then a certain value there, and you want to see how these different values are correlated. And notice that because of the Einstein equation, this is equivalent to look at fluctuations of the geometry. So for us, this would be equivalent to say, okay, I have a certain volume here and another volume there, or a certain curvature here and a certain curvature there. I want to see how they are correlated. So you can do it for a state like this one. Now we are happy, we have all agreed that this can model a cosmological state. We say that this is like a transition from nothing into something, but this is, but the reality is simply that this is a preferred states in the theory. And in order to compute things, of course, I have to do it numerically. I use the factorization that I have shown you this morning. And then I can compute on these states, I can compute observables, and observables are the usual one, just like area, volume, angles, and angles are associated also with a curvature. So I have these observables, and I can also look at the spread of these observables, and I can study correlations. And, and I can study the entanglement, the entanglement entropy that gives me an upper bound to the correlations. So we have studied this, and we had some results back in 2019, in which, first of all, we checked that our states was correctly representing a three-sphere, so the observables, namely the angles, were exactly the one that corresponds to a regular triangulation of three spheres. We saw fluctuations that were larger than what you would expect, and also we saw very large correlations. The problem with this is, so this was very exciting indeed. The problem with this is the fact that when you have a state like this with 5 tetrahedra all glued to another one, basically large correlations needs to be expected because each region is connected to all the others. So you wanted to do a refinement of your graph so that you can talk about regions that are disconnected, that are not really adjacent to one another. So we tried the refinement. So we did this, basically. Yep. And this. So we had 20 tetrahedra on the boundary. The problem is that even if you evolve things in this way, you still have a system that have the memory of the fact that everything was in interaction with everything. So the right thing to do, okay, is let me go directly. The right thing to do is to go here. So now you have a triangulation of the tree-sphere with 16 cells. And now some of the cells are adjacent, some of the cells are separated by an intermediate cell, and some of the cells are separated by 2 cells. So now you have a sense in which some cells are close to one another, we say sharing a phase means being in interactions, being adjacent, and you have a sense in which some cells are not. So we studied, again, the correlations of my observables here. So you can study how different nodes, so for instance, the curvature and the volume at the given nodes is correlated with curvature and volumes to other nodes. And this is the result we got so far. Unfortunately, we don't have a clear behavior so that we can say, oh, okay, correlations die the farther you are, and so on. This still needs to be understood better. But we have a technique. And again, we are in a situation in which more computations needs to be done, more understanding needs to be done, but we have a full setting in place. Wanted just to go back and add one more thing. So one of the things that we have been studying is the entanglement entropy. So the entanglement entropy, I told you, give an upper bound to the correlations. So that's why it's interesting for us in cosmology. And you can study the entanglement entropy by taking partitions in your states. So you decide, I take one region, say one tetrahedra, and I look at the entanglement entropy with respect to all the rest. Or I can take 2 tetrahedra and I look at the entanglement entropy with all the rest. So you can play this game and find some interesting results. And then the big goal is to connect this. So here it is. So you can take all the different partitions you want. But the big goal then is to connect whatever information you have with standard cosmology. So one of a master student working in our group, Sophie Reed, worked exactly on this, and then we got stuck because all our computations were done on a tree-sphere, and we discovered that there is not so much work in the literature, and this is astonishing. So you cannot find a good literature on perturbations on a tree-sphere. Everything is just for flat space. So most of the work went into defining perturbations in cosmology in that context. But again, what I want to say is that there is a roadmap of things that can be done, and there is more work to be done with the numerics. There is this interplay between going farther and farther with the numerics and getting more and more insights and getting more information about the physics of the transition amplitudes. And as I said, to me, understanding the core concepts, the core properties of the transition amplitudes is something that you can try to translate directly into phenomenological aspects of your theory in cosmology, for instance. And I want to close just with, again, an advertisement for the fact that, so you have these correlations in our first model with the 5 cells and with the 20 cells, the correlations were very high. We have to understand better the situation with the 16 cell. So the fact of having high correlations could be a challenge. So first of all, this is a proposal for a vacuum state of the initial geometry of the universe that is derived from scratch from the full theory. What people usually do in cosmology is to take a given cosmological scenario, in particular, consider a scenario in which you have inflation, and then by hand you attach an initial state that is the one that suits the kind of evolution. So here the perspective is different. We want to predict what is the vacuum state, possibly this one. So you predict the properties of this vacuum state, you predict the correlations and the entanglement entropy. So then if these correlations stand the proof in the future so that they are particularly high, this could challenge the inflationary scenario. So maybe inflation can be short, or maybe we can even get rid of inflation. But again, this is now in your hands, because if you can make sense better of this kind of model, maybe you can make more solid predictions. And once we have solid predictions, we can go to cosmologists and say, oh, look at this. So I close here and I take your questions.
Okay, thanks. Thanks, Francesca, for wonderful lectures. Probably we have some time for questions.
Hi, thank you for the very nice lecture. Can I go back again to ask about the bouncing scenario? Because I think this is one of the great success in loop quantum cosmology. But the way I see it, but correct me if I'm wrong, is this kind of thing has some kind of ambiguities in their interpretations, in the sense that...
you mean the spin-form one or the canonical one?
The bouncing results. I mean, like...
But the bouncing results in the spin-form theory, this one, or in the canonical theory?
In the spin-form.
Okay.
Can we because in the classical GR, we know that the theory is invariant under time reversal symmetry.
Yeah.
Can we interpret this result as, instead of having a universe which is initially contracting and then bouncing again, can we interpret it like there is nothing at the initial state, and then there is some two universe that expanding to the different branches?
So you want the transition from nothing into something. So this is also possible. Yeah. So the question is this transition more probable than the transition from something into something else? Yeah.
Nothing into two, that's what you're saying. You're saying to interpret this same transition here, not from one contractive expanding from nothing into two.
So you're saying you have
right?
sorry, let me do it like this, if I understand correctly. So here it's like we are saying there is a directionality that is this, or could be this, right? And you are saying, what about if I do this, but then, it's vice versa, actually. So you want to have maybe something like this, but also this.
Right, something like that, yes.
Again, directionality has to do with thermodynamics. So if you want really, and the fact that the transition amplitude, so okay, I can see the transition, so I can see this going this way and this going to this way. So this transition amplitude, this spin-form is representing both. So for the purple one, we agree. So what about the green one? Can I have that? So this would be like to transition one from nothing into something, and I think I have a counter argument for this. So I can see this. I can see this, and this, that would be, no, okay, now I understand better. If you do this that you are asking, okay, so I told you I am considering here one hypercube that corresponds to a contracting geometry and one hypercube that corresponds to an expanding geometry. If I do what you are asking, is as if I was computing the probability of one universe that is, so one hypercube that is expanding and one hypercube that is also expanding. So it's like a different thing, you see? So you're, or not. It's the same. It's the same. Yeah, but the interpretation is different. You have a, John. Yeah.
You could even make it even more interesting. You could say, what's the transition probability for transitioning from nothing to 3 universes? You know, you could and then what happens to directionality? I don't know. I think it's a very interesting question that nobody really thinks about.
What?
I don't think we have an answer to that.
There is those configurations. So there are 4 different configurations that you can compute from this simplex, including 2 of yours and 2 of. Because there is something called cosine problem or property of the spin form.
Oh, you're opening up a Pandora box now.
So this all of drawing purple and green, they all belongs to saddle points contributing the cosines.
Yeah. So let me answer in a different way. Let me be a bit pragmatic here, because the question is not whether this amplitude represents different thing. The question is, you want to describe a phenomenon. What is the corresponding spin network and spin form that represent this phenomenon? Does the same spin network represent other things? Yes, maybe. But maybe you are not interested in that, because you may look at the convergence with other pictures that you receive from general cosmology, from loop quantum cosmology, and so on. So you want to focus on those that are physical promising. So the kind of game that I like to play is this one. I have a physical picture. Can this physical picture be described with my theory? Oh, yes, I can. And I do this with this. Can this same equation describe something else? Okay, maybe, but maybe it's not interesting.
Thank you.
So back to the points on singularity resolution. There are sort of, I guess, 2 notions of singularities, right? There's geodesic incompleteness, and there are curvature, the divergences. And I know that like the relation between the 2 is not fully fleshed out even in the classical theory, but I was wondering if right now spin foams could say anything about singularities for like geodesic incompleteness, especially because 2 of the most important singularities that we would care about, black holes and cosmological singularities, are both geodesically incomplete and curvature divergent.
Yeah, Carlo wants to answer, but let me say something. When you compute, that's exactly one of the situations in which you have a tension between the canonical and the covariant framework, because in the covariant framework, all you can say is in terms of probabilities. So talking about geodesics implies that you can look at trajectories, and this is not what we do here. Carlo, you have more to say?
Yeah, I agree with what you're saying, but I think it's stronger. let's see the relevance of the notion we're using. You're saying, oh, singularities I can understand in terms of geodesic incompleteness, okay? Now, geodesic incompleteness makes sense on a Lorentz manifold, okay? So it only makes sense when there is a Lorentz manifold. In quantum gravity, there is no Lorentz manifold. Whatever you turn it around, there's no Lorentz manifold. The Lorentz manifold is just an approximation. So geodesic completeness is not the right way of studying the problem, period. I mean, you can ask, in a space-time that classically would evolve towards something where there is geodesic incompleteness, what's going to happen? But what's going to happen much before you get to the point where the geodesic is incomplete, you hit the singularity. Because much before you expect, the Lorentzian manifold approximation is not suitable for describing what happened in nature. So, careful, because some notions are perfectly good, fantastically, you can do theorems in classical GR, just they don't, the same notions just don't make sense once you go outside the classical domain.
Thank you.
Okay, so I think we have to make a break.
We have to close, but I want to highlight that I am around, you can ask me questions, but also the people who have been working on the results that I have presented are around. So you can, besides talk with me, you can also, you are allowed in a school of quantum gravity to go bother all the people whose results you are interested in. So do it, profit of these days.
Okay, so we have 20 minutes break, so we meet in, well, less than 20 minutes. So we meet at 3:40.